Hello, my name is Jean-Noel Moyne. I work at Synadia in Solutions and Engineering, and this video is about showing you how you can use the NATS CLI tool to run your own benchmarks of the NATS messaging system and of whatever target infrastructure you want to run it on. The NATS CLI is a companion tool to the NATS server, which you can find on GitHub. You can install it easily by just going to the release, finding the package that you need, and downloading it and installing it this way. Or if you have OS X, you can also use Brew to install this. So typically you would run benchmarks on your own target environments to see what kind of actual realistic performance you will get out of the machines, the network, the environment, pods, etc., that you are thinking to use in production. In this case, for demonstration purposes, I'm just going to use my anonymized machine. So it's a mid-2021 16-inch MacBook Pro Intel Garden variety. And for this, I'm going to run the NATS server, which you can find here, the NATS CLI tool, and the NATS top tool as well, you can find there. Okay, so now that the software is installed, let's run it. In this case here, as I said, I'm gonna make this demonstration just using my laptop. So I'm going to run the server by default, no configuration, just -js to enable JetStream and -m8822 to enable the monitoring port. I'm gonna leave that running in the background. I'm gonna run in this window a NATS stop. This connects through the monitoring port to the NATS server and gives you some information on what's going on with the NATS server. As client applications connect, you'll see them appear here with information of each connection. You can also monitor the CPU utilization of the NATS server process, the memory utilization, number of slow consumers, number of messages in and out, number of bytes in and out, current number of messages per second in and out, and current number of bytes per second in and out. Now, benchmarking with NATS Bench. You can use NATS Bench to produce two kinds of numbers. One is latency, the other one is throughput. Let's look first at latency. So the idea here is to be able to use NATS Bench to measure the round-trip time latency process to process introduced by NATS. So in this case, we're going to be using NATS Bench in request reply mode, where we start, in this case, just one single replier. So NATS Bench test the subject. We're going to be in a reply mode. We're going to use just one single thread or go routine to be precise. You could have as many of those as you want. They all make independent network connections to the NATS server processes. So they look like servers, or they could be multiple instances of NATS Bench on different machines, etc., etc. In this case, we're just gonna do literally a ping and back and see what the latency is. So what we're doing here is starting to generate some traffic. -bench subject test. We're gonna be in request mode, and we're gonna just use one go routine for this. As you can see, briefly you can see those two being connected there. It's going to send from a single thread one message, wait synchronously. So the message is gonna go from this process to the NATS server, to this process. This guy is just gonna return back a reply, an acknowledgement reply, as soon as it receives the message, and back out there, and so on. So this is synchronous back-to-back requests from a single thread. So we get a total number of messages per second of 7,500 about. And what this is interesting is then you can then use this to calculate what your average latency is. So in this case, that's 133 about microseconds on average of a round trip going back and forth of a NATS. Okay. Next thing we're gonna do is use NATS Bench to measure throughput. We're first going to measure that throughput using just Core NATS, so plain old publish subscribe. The simplest way to do this, we're doing bench again test, and we just simply, in this case, let's start with just having just a single publisher. So this goes very quickly. As a caveat, typically when you do benchmarks, you would want to do benchmarks that run for more than a fraction of a second, 30 seconds, a minute or more, so that you get a bit more of a sustained throughput rather than either a peak or something that's potentially influenced by something else happening during the partial part of a second during which the test is running. So as you can see here, as I run a couple of them, there's quite a bit of variation, a little bit of variation between the numbers. So, but in the case of this demonstration, I'm going to keep the number of messages in the runs relatively small, such as to not make the demo spend a lot of time waiting for benchmark runs to finish, which is more what the reality is. So by default here it's sending 100,000 messages and 128 bytes, so small messages, and this is the latency we get out of about for an average like almost 3.94 million messages per second. Right, then obviously not much interest in practice to publishing to something that no one subscribes to, so you can use just one instance of NATS Bench. Again, one publish go routine, one subscribe go routine, each making their own individual NATS connections to the server. So from the server's point of view, it doesn't even really know that they are in the same process. They could be two different processes on two different machines. And here we get an idea of what the throughput is going back and forth between. Again, because this is very small, I'm going to run a couple of them to get more of an idea of the variation being such that you can see here the first benchmark test, we got 3.9 million, then we got 4.2, and now we get 4 million. So long story short, in real life, you'd run longer running benchmarks, and you would do that by simply specifying a larger number of messages than the default of 100,000. So here we have a very simple one publisher, one subscriber. You can see total is 4 million or so around messages per second. Our throughput is about almost 500 megabytes per second, not very much. That's because though we're sending a lot of messages, obviously there are small messages, right? And in this case, the publication rate and subscription rate are more or less matched. Another thing we can do easily then now at this point is increase the fan out. So when you do pub 1 sub 10, you're creating 10 subscribers on that same subjects, which means that when you publish the message, you have one publishing thread. The NATS server is going to send 10 copies of that message to 10 different client connections. There again, we get the total aggregated rates, which is 5.3 million messages per second, about 650,000 megabytes per second. And you can see the publisher published at about 500,000 per second, and the subscribers are 480,000, right? And the subscribers, there's 10 of them. Each one of them subscribed at about the same rate, the 10 of them together making 4.8 million messages. And you can see also as well your maximum, minimum, average, and standard deviations for these, right? So here we've been able to show pretty decent throughput in number of messages per second, but not so much in terms of throughput. It's as expected because we're sending very small 128 byte messages, lots of overhead. Obviously, you're going to be CPU bound rather than bandwidth bound as your limit to what kind of number you get. So pretty easy to do this. You simply define a message size that is larger than 128. And you can also play around with different numbers of publishers and different numbers of subscribers. So for example, here taking a publisher of 2 publishing threads going at the same time, 4 subscribers, so it's a 1 to 4 fan out. We're gonna make this a little bit longer. Let's see, sorry if I can count. 1 million messages. and large as well, so we can at the same time have a look at what's going on here and what we're looking at a little bit more in detail. So running this test, you can see here we have a total of 6 connections to the server. 2 of them have no subscriptions. These would be our 2 publishers, each one of them publishing 500,000 messages, and 4 subscribers, each one receiving a copy of each one of those messages. You can see depending, there's a small amount of buffering happening, the matching number of bytes received and sent, a number of messages, and the overall for what's going on at the server gives us a little preview of what's going on. It's receiving 25,000 messages per second, around 26,000, and sending out 103 or so, which is equivalent to what we have here in our results. The total was 128,000 messages. It's 2 gigabytes per second, so a lot better. This machine can actually do a little bit more than that, but being an Intel laptop, MacBook Pro 8, I don't know if you can hear the fans going on at full speed, but it's not the best machine to typically use to get the best numbers in terms of performance, because as soon as you start running a few benchmarks, the temperature goes up and it throttles the CPU, frequency down, because it doesn't want to overheat the machine. But suffice to say, I invite you to run, that's the whole point, to run these tests on your machines and get what numbers you get out of this. What I'm getting here is just an indication of what could be. If I wait a little bit and let it cool down and run it again, we may get a little bit better performance on a second run. That's another rule, by the way, of running benchmarks. Do more than one benchmark, more than one run, and see there that allows you to eliminate the outliers, right? And you really want to look at large numbers and do averages to get a pretty good feel for what your actual, in real life, in practice, in production, on your target environment, what kind of numbers you would actually possibly get out of your setup. Let's finish the run. Same thing, but suffice to say, run this and play with the number of publishers, number of subscribers, size of messages, your environment, and see what you get out of this. So that concludes the part about testing Core NATS request reply and publish subscribe. Now moving to JetStream functionality. So while there is a certain amount of interoperability between Core NATS publishers and JetStream publishers, in order to for applications to benefit from the full functionality of JetStream, you'll want to be making JetStream publish calls rather than Core NATS publish calls to publish into a stream. The difference between the two being that a Core NATS publish is an operation that does not return any acknowledgement from the server, while a JetStream publish operation lets you get an acknowledgement that the message was properly received and persisted into the stream by the server at publication times. So let's do some publishing on JetStream. The way you enable publishing through JetStream mode is by setting the JetStream flag. And we're going to just have one publisher, and we're going to start with doing synchronous publications. As you can see there, this is pretty similar to the request reply latency benchmark before, except that rather than talking to another application through the NATS server, you're just talking to the NATS server, getting the acknowledgement back. The same as any kind of distributed request reply transport throughput limitations. Essentially, the throughput is affected by the round trip time, and the way to increase throughput in those situations is to either have a lot of clients that make synchronous connections or start using batching. So NATS Bench also allows you to test that. In this case, batch, you can even specify the batch that you want. So let's start starting with 10. Right, as you can see, it improves dramatically. Let's go a little bit further. 100, yet another massive improvement. We can go to 1,000. Some improvement, but not as much. So you start getting to where you have a diminishing return of increasing the pub size, the batch size, right? You can also try to simply use two publishers. This is equivalent to, in this case, with the default batch size of 100. And as you see, we get pretty close to the maximum size that we saw with batches of 1,000, except in this case we have two guys just using simply batches of a 100. You can at the same time still, for example, emulate observers, other Core NATS publishers being able to receive those messages published on the stream by simply subscribing to the message. Actually, I'm going to specify messages. As you can see, as we publish here, we still get pretty high rate. But those two, this guy here, and we can even try a fan out test. In this case, you can see how we start getting pretty high fan outs. So those are Core NATS subscribers onto the JetStream publisher. So right, so now that we have published data into our stream, you can see info and then stream. Oops, sorry. We can see what we have in that stream. So capture, we did a total of 700,000 publications here. Let's get data back out of there. Without getting too deep into the minutiae here, essentially the way you get data out of a stream in NATS with JetStream is by creating consumers. You can look at consumers as views onto the stream. They allow applications to use those consumers to either iterate and get copies of the data or a subset of the data that is stored into the stream. They have some state, kind of like a cursor if you want, indicating where they are through that iteration of the data in a stream. And if in the case of those consumers being acknowledged, meaning that the application must, upon reception of message reception and consumption and processing of the message, send back an acknowledgement or a negative acknowledgement or ask for more time, but in any case indicate that it is actively processing or has processed successfully or not the message. You can use a stream as a queue, as a working queue, where once a message has been properly acknowledged, it is removed from the stream. So essentially letting you use it as a stream, as a queue. Also, another thing about consumers, essentially simplifying again, two kinds of consumers. You have what are called ephemeral consumers and durable consumers. To simplify again, cover two broad kinds of use cases. You have the use case of some instance of an application coming up and needing to get the current state of like all of the messages, for example, in a stream. So this is one instance of a specific application getting its own copy of the data. And you can have any number of those applications coming at any given time, and all of them request at their speed, at their time, and consuming in a flow control manner all of these data, so copies of the data from the stream. And then the consumer disappears because they are done, or they keep it alive while they're running, but as soon as the application quits, then that consumer disappears. The other kind of consumers are durable consumers. The idea there is that they are consumers that are used in a shared way by multiple instances of the applications. So this would be the case of, for example, you have a lot of data in a stream and you decide at some point in time to process in parallel all of the data in the stream. So in this case, you would use a durable consumer, have many instances of your applications, use that single durable consumers. And the durable consumer essentially acts as a queue for distribution purposes, as it distributes the messages between all of those instance applications using and consuming from that durable consumer. So let me show you first the case of the ephemeral consumers, which are specifically ordered push consumers. So very similar to the traditional pub/sub, right? In the sense that you can have as many subscribers as you want. Let me put the subject first. And each one of them would get their own copy of the messages in the stream. So in this case, let's go and read all of them. There we go. Oh, sorry, my mistake. Too many. There we go. This is one instance of an app coming and saying, hey, give me, in this case, all of the messages from the start of the stream. for 700,000 worth of it, and getting some copy. You can again see some emulations, not as much as a fan out as two independent applications coming out at once, and each requesting for their own copy of the data that they iterate at their own speed. Again, this is flow controlled, and all getting their own copy of it. Here we get some pretty high number, obviously 1.2, whatever, 1.3 million messages. This is distributing 7 million messages total, right? Because it's 10 guys receiving their own copy, 7,000. The second type of consumers I explained are durable consumers. And in this case, again, to simplify to the best way to use them, it is using a pool consumer. So when you define -pool, that means that instead of having a ephemeral subscriber, which gets all the data and there's no acknowledgement whatsoever from the application onto iterating through that data, you're getting a process here where this subscriber here pulls, in this case, a certain amount of messages at a time. So unlike push consumer, you can specify a batch, which again is going to be key in the use cases where you know you have a lot of data to iterate through in that stream, and you want to leverage batching for higher throughput. And it's not just batching to get data faster into a single instant application pooling from that pool consumer, but also because a lot of the time the processing involves actually, doing something with the data and sending it somewhere else or writing it to something else like a database. So if you can receive from a very high rate from your messaging system, but you end up writing one by one to, for example, a database without batching things, then you would never be able to keep up. So the ability to indicate that you're willing to go to a certain amount of batching if there are so many messages available in stream means that you can just process them at once and send them out, or persist them for them as once and get higher throughput on the way out of your processing as well as on the way in. So again, this is the extreme here of a single thread, one by one, right? Pulling each messages, sending back an acknowledgement, and then making another request to pull, saying it's indicated interested in yet another message. So we're not going to be using very much CPU at all. This is obviously, we're limiting ourselves by the fact in this particular test that we're reading 700,000 messages with just one single consumer, and something that is designed to provide horizontal scalability. In the end, that's what pool consumers do, is they allow you to scale out horizontally. Or if you have less machines but are able to process faster a lot of messages at once with higher throughputs, you can then use batching as well. So let's go and go obviously to something like 100, which we know is pretty good, and obviously huge impact in the performance. So this is pooling. One guy pulling things by batches 100, but obviously where you can even go faster is if you do, obviously I have only so many cores on my laptop, but sorry, my bad. Use more of them, and yet again speed increases going from 210 to 272. If I had more than just a single laptop that's starting to overheat, I would obviously be able to scale a lot further than that. Again, horizontal scalability is the name of the game here. And finally, to finish, I want to just show you how these tests being done by default were done using memory with replication of one, so only no replication, essentially only one replica total in a cluster. But you can certainly change this by using -- replicas or -- file storage. But something to be aware of is that the first time you run this bench in the JetStream mode on a particular subject test here, it will automatically, as we saw, create that stream called bench stream, right? And you will not delete it. The idea being that you can run NATS bench a few times to publish data into the stream, you don't want it to delete the stream at the end, because that would delete all the data. So you couldn't later on do pull or push consumers and to measure the speed of retrieving data from or a copy of the data from the stream. When you do something such as, for example, wanting here to change to file storage rather than memory, just simply remember to remove the stream. That's the simplest thing, is to delete it. And here you can even force it like that, so it doesn't prompt you for anything. And then we can do another test in JS mode, this time with storage file, right? For example, oops, my bad. Let me say it's 4 publishers. And there we go. This was done again, storing to file rather than memory. So if you remember from before, you get less performance. But what's kind of interesting is, I'll do it quickly here for, let's load up like 400,000, so we have a little bit more. Sorry. Retrieving. So what's interesting is that actually retrieving from disks is still quite fast. So this is again, right, in this case, push consumers. So we're sending 4 times 400,000 messages in about 4 seconds. So sending at about 400,000 per second. The same goes again if you were to play with using pull consumers as well, rather than push. And in this case, the message is actually properly consumed. So you see it's a little bit slower because of the acknowledgements, but you get a much higher quality of service. And that's it. Much more you can do with. Remember, you can always, do this and use the cheat sheets as well to get some examples of all the options and how you can use them. Thank you very much for watching this video.